Hello everyone, in this video we will be solving a simple Rankine cycle problem using a Matlab code. The first thing we will have to do is to download the Xtheme function. So the Xtheme function will be used to replace, if you want, the property tables. When we'll be looking for, let's say, the enthalpy at specific states, we don't need a table, we will just have to call the function Xtheme. In order to get Xtheme function, you have two options. The first one is you go to MathWorks and you directly download the Xtheme function. The second option is that you go to GitHub, and here you have different other options to get it for Excel file, MATLAB, OpenOffice here, and Scilab. Okay. Scilab is if you want, an open source version of MATLAB, okay, or similar to MATLAB. After you do this, you will be downloading the code, but at the same time a user manual. So the user manual is here. So, and you will see that using Xtheme function is quite easy. So you just call Xtheme. Then you tell Xtheme what you are looking for example, enthalpy, entropy, or whatever, underscore the properties you will be using to get this, okay? You remember that the state postulate is telling us that we need two independent intensive properties, so you will be listing them here. And then the numerical values of the properties that you will be using. Here you have a simple example listed. For example, if you are looking for the density, so the inverse of the specific volume, at a pressure of 1 bar and 200 degrees C, here you have to be careful because the pressure in Xtheme is in bar. So all the values that we have in our Rankine cycle in kilopascal or megapascal have to be converted to bar, okay? So if you want to know the row, so you write row, which is what you are looking for. I would like to get the density knowing pressure and temperature as inputs. The pressure is 1 bar, the temperature is 200 degrees C. That's it, okay? And then you can do this for several other properties, so temperature, pressure, enthalpy. Here I'm highlighting the different enthalpies or properties that we will be using to solve our Rankine cycle. Specific volume is here. Entropy, we will need it, for example, to state that S3 is equal to S4. And what we will also try to monitor while solving our Rankine cycle and also changing, trying to improve the efficiency of our Rankine cycle by reducing the pressure in the condenser, increasing the maximal temperature, or increasing the pressure in the boiler, is to check what is the quality. And the quality here is vapor fraction, X. And you'll see here that we can get X knowing pressure and entropy. So this is all what you have to know about Xtheme. The next step is to go to MATLAB. So for example, if we want to know the enthalpy at state 3, H3 for example, and we know in our problem that the pressure was 2 megapascal and the temperature was 400 degrees C. So let's call Xtheme. Okay, what are we looking for? We are looking for the enthalpy underscore what are the inputs, pressure and temperature. What's the value of the pressure? It's 2 megapascal. Here you have to be careful. You have to convert your 2 megapascal to bar, knowing that 1 bar is 100 kilopascal, so your 2 megapascal will become 20 bar. What is our temperature? 400 degrees C. And here is directly my enthalpy in kilojoules per kilograms without using any table. Now the next step is to start our code. So we are coding a simple Rankine cycle. The first thing we'll have to do is to set our inputs, okay? What do we know? We know the pressure in the condenser, let's call it P1 at state 1, is equal 10 kilopascal. What does it mean, 10 kilopascal in bar? This means 0.1 bar. Also, we know the maximal temperature in the cycle, and this is at state 3. T3 is equal, for the moment, 400 degrees C. We also know the pressure in the boiler, the maximal pressure. So the pressure in the boiler, and we'll be calling this P3, okay? P3 is equal to 2 megapascal. We said 2 megapascal is 20 bar, okay? So now, after we have done this, we can start calculating the work of the pump, Q in, the work of the turbine, and so on, okay? So here I'm using like the classical way, okay, step-by-step approach. And to calculate the work of the pump, we will be using minus the integral of V dP, okay? So computation of the work of the pump. So what do we know? We know that the work of the pump is equal to what? Is equal to minus the integral of V dP, knowing that V will be constant because it's compressed liquid. So this will give us simply minus V1 cross P2 minus P1, right? Okay. So, do we know P1? Yes, we do. But P2, we don't know it, okay? But interestingly enough, P2, this is the inlet of the boiler. So we know that P2 is equal to P3. So let's write it here. P2 is equal to P3. We don't know V1. This is something we will have to get. The other problem is that, if you remember well, the pressures are in bar. But we would like to have the work of the pump in kilojoules per kilograms. So we have to convert the pressure back to kilopascals. So now we multiply by 100. Now the only thing missing is that we have to know the specific volume V1, okay? To get V1, what do we know? We know that V1 is the specific volume at a pressure of 10 kilopascal, so 0.1 bar, or P1, and at the same time, it's for x is equal 0, okay? We can use here our user manual. We just have to go to specific volume, and you see here that saturated liquid volume, or specific volume. So here we need to write VL underscore P. Do we know the pressure? Yes, we do. This is P1. So we can write here, we call Xtheme, and what we are looking for is specific volume, and it's of the liquid, of the saturated liquid, knowing only the pressure. By putting L here, we are actually stating indirectly that X is equal 0. And this is for pressure P1, okay? So if you see, if we just run this, okay, so we get directly our work of the pump, okay, minus 2 kilojoules per kilograms, okay? So now we keep going. The next thing to calculate is the heat in, Q in. So computation of Qn. What do we know? We know that our Qn, okay, I'll write small qn, is equal to what? Following the first law of thermodynamics, we know that this is equal to H3 minus H2, right? Do we know H2 and H3? No, we don't. So therefore, we will have to calculate them. Starting with H3, which is the easiest one. H3 is equal to what? This is the enthalpy at 400 degrees C and 2 megapascal. We call Xtheme again. and we say, okay, give me the enthalpy, knowing pressure and temperature. What is the value of my pressure? The pressure is 2 megapascals, so this is P3. And what's the temperature? T3. So this is done. Now to get H2, H2 is equal to what? Here we have different options, okay? The easiest one was to neglect the work of the pump, and therefore H2 will be equal to H1. But here, since we are calculating the work of the pump, we can still use it. So H2, following the first law of thermodynamics, if you take the pump as a control volume, it's equal to H1 minus the work of the pump that we have already calculated. So now the problem is not to get H2, is simply to get H1. So H1 is equal to what? What do we know? We know that H1 is the enthalpy of the saturated liquid at 10 kilopascal. So we'll use the same logic as here. Xtheme. And what we are looking for the enthalpy of the saturated liquid, knowing the pressure with pressure as inlet and at pressure P1. Okay, we know H1, H1 will give us H2, we know H3, it's fine. So let's run it, and you see here we have work of the pump, Qn, and this is our Qn, 3054.4 kilojoules per kilograms. Then the next step is computation of the work of the turbine. What do we know again? Work of the turbine is equal to what? Following the first law of thermodynamics, we know that work of the turbine will be equal to H3 minus H4, okay? So obviously here we are neglecting the variations in potential energy, kinetic energy, and we are assuming that the turbine is isentropic. So do we know H3? Yes, we do. It's right here, okay? So now the game is to get H4. So, but H4, to get H4, since the process is isentropic, so therefore we need to calculate first the entropy at state 3, stating then that S4 is equal to S3, and then we can use the enthalpy knowing the pressure, 10 kilopascals, and the entropy, S4 is equal to S3. So basically what we are writing is that H4 is equal to H at 10 kilopascal and S4 is equal to S3. Okay, so we'll work a bit backwards. We said S4 is equal to S3. Do we know the entropy? No, we don't. So we have to calculate S3. And for this, we call again Xtheme function, Xtheme. And what are we looking for here is our entropy. And as inputs, we have pressure and temperature, our 2 megapascals and 400 degrees C. So 20 bar again and 400 degrees C. So this will give us S3. Here we are claiming that S4 is equal to S3. And then now we can get the enthalpy. And it's Xtheme. What are we looking for? We are looking for the enthalpy, knowing the following properties: pressure and entropy. Okay? So if you have a doubt, you just can go here and you see enthalpy, pressure, and entropy. Enthalpy as a function of pressure and entropy. So this is what we are doing here. What is the value of our pressure? Our pressure is P4, okay? And our entropy is S4. Do we know S4? Yes, we do. We are calculating this here. Do we know P4? Well, actually, we don't. But we know that P4 is exactly equal to P1, so we can write it here. And this will fix our problem, okay? So here with this, we will get the work of the pump, the Qn, and the work of the turbine. The last thing we need to get is the thermal efficiency. So computation of the thermal efficiency. So therefore, we'll be writing the efficiency of the cycle is equal to what? Is equal to the work of our turbine minus, I will put minus, but I will have the work of the pump, the absolute values, okay? Or I can put just plus, okay, if I want. So the work of this divided by Qn, our Qn, okay? And just to get this kind of a percentage, I will multiply by 100. So we have everything here. We'll just erase this. And let's go. And you see we have everything we need. The work of the pump minus 2 kilojoules per kilograms, Q in 3054.4, work of the turbine 989.65 kilojoules per kilograms, and here is our thermal efficiency, okay? We said also that we are interested in checking what is the quality at the exit of the turbine, so let's add this line. So computation of the quality at the exit of the turbine. Okay, here what we are looking for X4, okay, and X4 we just have to call Xtheme again, Xtheme function. What we are looking for, we are looking for our quality X. What do we know at state 4? We know again the pressure, P4, and we know that S4 is equal to S3, so pressure entropy with P4 and S4, okay? And now we have everything we need, right? The work of the pump, Qn, work of the turbine, efficiency, and here is our quality, okay? So this is for the simple normal Rankine cycle. Now that we have this, and you see that it takes a bit of time to code this, okay? But the beauty now is that we can start playing with the different parameters without solving the problem again and going searching for values in a table again and again, okay? So now we know that the efficiency 32.33, and this is what we have to check. So now let's assume we would like to reduce the pressure in the condenser down to 4 kilopascal, okay? So meaning we just have to change P1 here. 4 kilopascal means 004 bar. And we keep all the rest constant. So you see it's as is as this. We save, we clean up a bit here, and we run. And we see we have actually here an increase in the work of the turbine, 1,100. The previous one was 989. The thermal efficiency increases from 32.32 to around 35%. And here what we have a reduction in the quality. The previous value was 0.86 or 86%, and now we are reducing our quality to 83, okay? So this is something we don't really like, okay? Now if we would like to try, let's say, another possibility, let's try to increase the maximal temperature. So we put the pressure back to 10 kilopascal, and we increase our maximal temperature to 600 degrees C instead of 400 degrees C. I just run again. The work of the pump doesn't change. the Qn increases significantly from 3054 to 3496.9. The work of the turbine increases also, which is expected. And here we have the efficiency also increasing. So, and we have also a quality that is increasing significantly. Okay? Here actually, when you look at this, I have just noticed that I made a mistake here. Where is the mistake? Is that here I kept 400, okay? So to avoid this, I will just write T3, and here I will write as P3, okay? Because I updated the value here, but it didn't updated it here, okay? So let's run it again. But at least you can also check other options like this. So here, what we have the new Qn, the work of the turbine. Here is a new efficiency, 35.65 compared to 32.32. This represents roughly an increase in 10% of the thermal efficiency and a boost in the quality up to 0.94 compared to our 0.86 under previous conditions, okay? We know that this is basically the best solution, right? And even conceptually, we know that Carnot is telling us that what governs the maximal efficiency of a Carnot cycle is T1 over T3. The more you maximize T3, the more actually you increase your Carnot efficiency, and you also increase the efficiency of your simple Rankine cycle. However, we have some limitations in terms of material properties, is that we cannot exceed 750 degrees C, okay? So the last one that we will be trying is we keep everything constant, but we will change the pressure in the boiler, okay? Instead of having 2 megapascal, we will increase it to 4 megapascal, okay? 4 megapascal means 40 bar. Okay, and now we can run it again. And here basically you see again that we have an increase, but we have to be fair, meaning that here we change P3, but we kept T3 high, meaning that here we are changing two properties. To be fair, we have to change the pressure in the boiler, but bring back T3 to the maximal temperature that we use in the previous case, okay, 400. So here we will see the independent effect of an increase in the pressure in the boiler, okay? So if we run this, you see that the pressure is increasing, so the work of the pump is increasing. We have an increase also in, a decrease, sorry, in Qn compared to our 3054, an increase in the work of the turbine, and an increase in the thermal efficiency, okay, up to 35.31. This represents also around 9 to 10% increase in thermal efficiency. However, here a red flag, our quality is going down. So from 0.86 under the previous normal conditions down to 0.81 or 0.82, okay? So this is something that we really don't want. So the idea here is that you can see that by just using a function Xtheme, you can solve your problem rapidly, and you can solve it for different inputs, okay? In an ideal case, you will be taking, let's say, different values of maximal temperature, maximal pressure in the boiler, and then you have a plot of thermal efficiency as a function of the different values of temperature and pressure and so on, okay? The last thing I would like to show you here is the impact of the pressure in the work of the pump, okay? So here what I will be doing, I will put this back to 2 megapascal. Everything is normal here as in our previous case. The only difference is that I will force this to be equal to 0. Okay, so I'm neglecting the work of the pump, the 2 kilojoules per kilograms. compared to the work of the turbine, the 989 kilojoules per kilograms, okay? So here this is 0, so here the consequence is that H2 will be equal directly to H1, right? And here the work of the pump is 0, and you see that our thermal efficiency is 32.38%, while if you consider the work of the pump, it will be 32.32. So this is definitely negligible. So in the future, we will always neglect the work of the pump compared to the work of the of the turbine in a Rankine cycle. Thank you.